Okay, so get this. Um, Imagine, like, you look at a tree
Mm.
and you instantly know where every other tree in the forest is,
Wow.
even like miles away.
Yeah.
Sounds kind of crazy, right?
Yeah.
Well, that's kind of the headspace we're in for this deep dive
Yeah,
into one of the biggest questions in physics.
definitely.
Like, what even is reality?
Right.
So we're going way back to 1935.
Mm-hmm.
There's this paper by, some big names,
Really,
Einstein, Podolsky, and Rosen.
big EPR paper.
Exactly. And this thing, it really shook things up
It did.
because they were basically saying, hold on a second.
Yeah.
Is quantum mechanics, like, really telling us the whole story?
Like, is it really complete?
Yeah, is it? So to get into this, we got to talk about entanglement.
Okay, so imagine like two particles, they
Okay.
get all tangled up, and they're linked, but then they're separated.
Okay.
And they can be really, really far apart.
Like across the universe far.
Yeah, exactly. But they stay connected somehow.
Whoa.
Right. And here's the thing.
Okay.
Quantum mechanics says if you measure, let's say, the momentum
Momentum.
of one of these particles,
Mm-hmm.
boom, you instantly know the momentum of the other one.
Wait, what?
Yeah, without even measuring it.
But how? Is that even possible?
Well, that's what puzzled Einstein.
Yeah.
He called it spooky action at a distance.
Spooky action.
Yeah, because it's like they're talking to each other.
Faster than light.
Right. And that just, like, breaks physics,
Yeah.
you know?
So either quantum mechanics is missing something,
Like a big piece of the puzzle,
or information can travel instantly across any distance.
which is mind-blowing.
Totally.
Yeah.
So what did EPR think?
Well, they thought quantum mechanics, as it stood,
Yeah.
was incomplete.
Yeah.
Like, there had to be hidden variables.
Hidden variables. What are those?
Like, things we couldn't see or measure yet, but
Yeah.
that would explain this connection.
Without the spooky action.
Yeah, exactly. They wanted to find a way to make sense of it all.
Right. Without turning everything we thought we knew upside down.
Exactly. And they came up with this criterion.
The criterion.
Yeah, for what makes something physically real.
Okay. I'm listening.
They said, if you can predict something with total certainty
Mhm.
without messing with the system,
Okay.
then that thing is part of physical reality.
But how does that apply to the entangled particles?
Well, think about it.
Okay.
We measure one particle's momentum.
Right.
We know the other one's, right?
Right. Instantly.
So they're saying that means the other particle's momentum was already real.
Even though we didn't measure it.
Yeah, even though quantum mechanics doesn't say so.
So either quantum mechanics is wrong.
Or reality is a lot weirder than we thought.
Yeah. It seems like we can't have both.
Right, and that's what EPR really nailed.
They forced everyone to face this crazy paradox.
Right at the heart of quantum mechanics.
Yeah, and like, what does it all mean for what's real?
Right, for reality itself.
This is getting deep.
Yeah, it is.
Okay, so this EPR paper, it wasn't just like a thought experiment, right?
No.
Like, did it lead to actual, like, real experiments
Oh, yeah, absolutely.
to test this whole spooky action thing?
Yeah, because the EPR paper, it didn't disprove quantum mechanics,
Right.
but it kind of exposed this big mystery that really needed to be looked into.
So, like, how do you even test something that weird?
Well, that's where Bell's theorem comes in.
Bell's theorem.
Yeah, it's this theorem developed by John Stuart Bell
Okay.
back in the 60s.
Okay.
And it basically gave physicists a way to test these ideas experimentally.
Okay, so, like, a way to see if spooky action was real or not?
Yeah, exactly, like a litmus test.
The litmus test for spooky action. I like that.
Yeah, it let them measure the correlations
That's
between
nice.
these entangled particles
Okay.
and see if they were as strong as quantum mechanics said,
Mm-hmm.
or if maybe there were, like, hidden variables.
Oh, right. Those hid variables again.
Yeah, that could explain things more classically.
So what did these experiments show?
Well, they've been repeated and refined over, like, decades,
Wow.
and they overwhelmingly support quantum mechanics.
Really?
Yeah, the correlations, they're way too strong
Wow.
to be explained by any theory that relies on local realism.
Hold on. Local realism. What's that?
So local realism is this idea
Yeah.
that things can only be influenced by their immediate surroundings,
Okay, that makes sense.
and that objects, they have definite properties even
Yeah.
when we're not looking at them.
Yeah.
It's kind of like our everyday intuition about the world.
Right.
But it seems quantum mechanics doesn't quite follow those rules.
So these experiments are telling us that the world is non-local.
That's what it looks like.
So things can be
Yeah.
connected in ways that like, don't make sense to us.
Yeah, that seem to go beyond our normal ideas of space and time.
That's wild.
Yeah.
So I guess Einstein was wrong then.
I mean, it's not so much that he was wrong. His paper, the EPR paper,
Yeah.
it was super insightful.
Okay.
It really highlighted this profound paradox
Okay.
right at the heart of quantum mechanics.
Mm-hmm.
And, even though the experiments,
Yeah.
they've mostly sided with quantum mechanics,
Right.
the debate about how to interpret it all
Yeah.
and what it means for reality,
Yeah.
it's still going on today.
So we've done these experiments, and quantum mechanics, it checks out,
It does.
but we still don't really understand what's going on.
There's still so much we don't know.
It's like we have the answer,
Right.
but we don't get what it means.
Yeah, that's a great way to put it.
Like we solved the equation, but
Yeah.
we don't get the concept.
Yeah, the EPR paradox, it opened up this whole new way of thinking about the universe.
Yeah.
And it forces us to, grapple with some really deep questions.
About reality itself.
Yeah, about what's real, about how we measure things.
This is some heavy stuff.
It is, but it's exciting, too.
Yeah, it's definitely mind-blowing.
It reminds us that science is a journey,
Yeah.
It's not just about finding the answers,
Right.
but it's about asking the right questions and being open to the possibility
Right.
that the universe might be way stranger
Yeah.
and more wonderful
Yeah.
than we could have ever imagined.
Okay, so this is all fascinating.
Yeah.
All this entanglement, spooky action.
Mm-hmm.
But I gotta ask, why should we care?
Right.
Why does this matter to, the average person?
Well, I think the EPR paradox, it challenges us
Are you-
to rethink our assumptions about reality.
Yeah.
It suggests that things might be way more interconnected than we
yes.
usually think. And it encourages us to, question what we think we know and embrace the mysteries that are still out there.
It's a reminder that the universe is still full of surprises.
Exactly.
So where does this leave us? If things can be linked like this,
Yeah.
what else is possible?
That's the big question. The EPR paradox, it's sparked all this research into how we can actually use cease entanglement.
Use it?
Yeah, like in quantum computers.
Oh, wow. Quantum
They can totally revolutionize everything.
Really?
Medicine, materials, AI, you name it.
So this isn't just theoretical anymore.
Nope, it's getting real.
So this spooky action could actually, do stuff.
Absolutely.
It's kind of crazy to think.
Yeah.
It all started with Einstein, trying to debunk quantum mechanics.
And it opened up this whole new world.
It shows you can be a genius,
Mm,
and the universe can still surprise you.
for sure. It reminds us that science, it's full of twists and turns.
Mhm.
Sometimes the biggest discoveries
Yeah.
come from challenging what we think we know.
Speaking of challenging what we know,
Yeah.
one thing that's been bugging me,
Okay.
does this mean nothing is truly independent?
Mm.
Is everything connected somehow?
That's a big one. There's still debate about it. Different interpretations of quantum mechanics have different answers.
Okay.
Some physicists, they think entanglement means everything's connected,
Whoa.
at a deep level.
Yeah.
Others say it's more about correlations between measurements,
Mhm.
not necessarily some deep connection between the objects themselves.
So even though we've seen entanglement in experiments,
Right.
we still don't know what it means for, the big picture.
Yeah, the EPR paradox, it opened up this whole can of worms.
Philosophically.
Yeah, about reality, cause and effect, even free will.
This is next level stuff.
It is, but it's exciting.
Yeah, it's definitely making me think.
That's what it's all about.
So for listeners, maybe feeling a little overwhelmed,
Yeah.
what's the main takeaway?
I'd say the EPR paradox shows us the universe is full of surprises. It says, hey, reality might be way weirder than you think
Right.
and more interconnected.
Yeah.
It challenges us to think bigger
Okay.
and to embrace the mystery of it all.
The more you know, the more you realize you don't know.
Exactly. The EPR paradox, it's a perfect example of that.
It's humbling,
Yeah.
to realize even our best ideas can be challenged,
Mm-hmm.
and that the universe still has secrets.
Definitely.
Well, I don't know about you, but after this deep dive,
Yeah.
I'm feeling kind of mind blown,
Mm-hmm.
but also really inspired.
That's the goal.
It's amazing to think we live in a universe
Yeah.
that's so complex and awesome.
And who knows what other discoveries are out there.
Right. So to our listeners, we leave you with this.
Okay.
If reality might be more connected than we think,
Yeah.
what other possibilities does that open up?
Mm.
What other mysteries are waiting?
Good question.
Keep questioning, keep exploring,
Yeah.
and who knows what you might find.
Exactly.
Thanks for joining us on this deep dive.
Yeah, thanks everyone.
We'll catch you next time.